Okay, guys, let's start and see how it goes. Last class, so what I tried to do is to figure out what are going to be the SLCs for the ammonia molecule using the 3 hydrogen atoms. One s orbitals are as a base. Okay, so the way we have separated out, we separate this as a ligand orbital, and then we have taken this basis, and what we found out that a reducible representation was something like 3, then 0, 1. Right. So then if we reduce this systematically, then the reduction was something like A1 plus E. So that is A1 is one dimension and E is doubly degenerate representation. So therefore, we would expect that using 1s orbital, we are going to get 3 SLCs. One of them is going to be totally symmetric, that already you have seen in the previous session, and 2 of them are going to be E-type, right? So that means doubly degenerate, and we have worked out for one of them, and we'll see what is going to be the second one. Right? So that's what we tried to do in the last session. So this was the SLC for the A1 type, right? That is 1 by square root of 3, and then all the positive combination of this 1 is A plus 1 is B plus 1 is C. Okay, so that is the normalized SALC of A1 type. Then we went for the to find out one of the E, right? And there also we found out this was without normalization, and then when we did the normalization, we got this is going to be 1 by square root of 6, and then 2 into 1 is A minus 1 is B minus 1 is C. So this normalization just for connectivity with the previous class, if you get this function when you do the normalization, that means integral psi star psi, so you are multiplying this function, right? So that is basically 2 into 2, so that is 2 square, so that is 4, and then this is going to be plus 1 and this plus 1, so total is 6, and then if you are taking the square root of that, so that comes like 1 by square root of 6 and this function, right? So this is one of the SALC of doubly degenerate representation E, right? Now what is going to be the second one, right? So that's what we are going to start now. So as it is a doubly degenerate representation, we should start with 2 different bases. And one we have started with a 1s A, and that is going to give you this one. Now if we start with 1s B, then what we are going to get it, right? Okay, so here you go, like 1 is B, I'm taking basis. Look at here, this is of doubly degenerate representation, of course, but I am taking the basis as 1 is B. Right? Now if we do this, then what we get, again we perform all the operations of this C3b point group on 1 is B, right? So identity, of course, like this remains 1 is B, right? So therefore I'm going to write this is going to be 1 is B, right? And then if I do C3 once, so that is going to go like here, so that is going to be 1 is C, so that is going to be 1 is C. Now C3 twice, this is comes once here coming, when I do twice it goes there, so that is going to be 1 is A. Okay, now sigma VA. So sigma VA means this is going to be the vertical plane which contains the atom A. So that is this one. So if we take this plane, so that is XZ plane, then 1s A becomes 1s C, right? So that is going to be 1s C. Now if I go for sigma VB, so that means it contains the atom B. So therefore, this is the plane I'm looking about, and then therefore this function remains unchanged, right? So that is going to be 1s B itself. And now last one, if I go for this sigma VC, so this function, this plane, which contains the one hydrogen atom C, so then 1s B is going to be 1s A. Okay, so now we go for the character. So character going to be for identity is going to be 2. For doubly degenerate representation E, this is going to be -1. This is going to be -1 because they belong to the same class, so their characters are going to be same. And this is going to be, all of them are going to be 0. Now if I multiply them, what we get exactly like that, 2 into 1s B, this is minus 1s C minus 1s A, and these are going to be 0 because I'm multiplying with 0. Right, so this means I have operation which is the first line, then I'm multiplying with the character, so that is the second line, and this is the result. So then what we get is that if we now do the sum over all the operation, right? So this is the summation. If I do it, what we get is that this one, right? So that is 2 into 1s B function minus 1s C minus 1s A, right? So just be vigilant that the last function what we did using the 1s A was, this was 1s A, right? Then minus 1s B minus 1s C, and this one is, when we started with 1s B, so that is going to be 2 into 1s B minus 1s C minus 1s A, right? And this is also not normalized, so we have to normalize this. If you normalize this, the function, what you get, normalized function, is exactly following the previous one. Is going to be 1 by square root of 6, 2 into 1s B minus 1s C minus 1s A, right? Exactly in the same way what we have done the earlier. Okay, so this is the second function of doubly degenerate representation E. Now comes the question, like when we get this doubly degenerate, what do we expect? Like this is one of the doubly degenerate function, this is another doubly degenerate function, so that's why I have given psi 1 E and psi 2 E, right? Now the question is that, are you going to accept these functions, right? Are these functions acceptable? Answer, of course, I mean, like if you just look at a little bit carefully, answer is big no, right? Of course, you might be thinking why I'm saying no. After doing so much calculation, we got this function, and then you are saying that these are not acceptable. Okay. Now, here is the important theorem I'm going to discuss, which is very important for your NET exams, GATE exams. So, we'll go a little bit slow, but it takes time. But I think it is useful to discuss it here. Right. So, I hope you, in case Professor Boliram did not discuss it, let's just recapitulate it. What what we are going to do it here. So these functions are not orthogonal, right? So therefore, we really cannot accept these two functions as such, what you are looking at on the screen. So what we have to do, we have to use the Smith orthogonalization, and using that Smith orthogonalization, we should be able to go and get the acceptable functions of W degenerate representation E. Now, what is this actually theorem says, or the Smith orthogonalization says? If we have two degenerate functions and they may not be orthogonal, but their linear combinations, if we can take in a proper way, those functions may be orthogonal, right? So let me just discuss this little bit. Let's say I'm having an operator A, and I am having two functions, psi1 with an eigenvalue A and psi1. Again, as it is degenerate function, so I am having another function psi2, and they degenerate, so their eigenvalue will be same. So that eigenvalue is A, and then I'm going to get the function by psi2, right? So what this theorem says, psi1 and psi2, they are two degenerate functions. They are not orthogonal, we can take their linear combinations, which may be orthogonal, right? So that means if I take it here, so that means psi1 and psi2, they are not orthogonal. So that means if we multiply them and do the integration, that doesn't give it to 0. But let's say I'm taking two functions. One is psi1 itself, whatever it is, and the other function, I'm taking the linear combination. That is, I'm giving psi2 prime, just giving prime because I'm taking the linear combination of, let's say that is C into psi1 plus 1 into psi2. So I have liberty to take my coefficients, right? Right, so these are the, so psi1 and psi2, they are not orthogonal, or they may not be orthogonal. They may be or they may not be orthogonal. Now here we realize that these two are not orthogonal, although they are degenerate functions. So so they are not orthogonal. But if we take their linear combination in a way that they may be orthogonal, right? So that means here what I'm going to say is that this is psi1 star, that is actually the formula goes, but these are all real functions, so we don't have to worry about this. Psi2 prime d tau, this I can write as delta ij, right? So that is going to be either 1 or 0. So let me write this can be delta 1, 2, right? So this is kind of orthonormal function. So they have to be normalized also because they are already normalized. So they have to be orthogonal. So that is orthonormal function we are going to look at here. Now, if we do this, so that means what I'm going to do, I'm going to use psi1 directly here, and then psi2 dash, this one, right? So that is going to be orthonormal function, right? So this is basically the idea we are going to use this, and then whatever the coefficient of C value we are going to evaluate, right? So from that we should be able to find out what is going to be the value of C. Now once we get this C and put it back here, take their combination, the new psi2 prime is going to be orthogonal to this one, right? So that is basically the statement of Smith orthogonalization. Now we'll try to see for these two functions what is the value of the C is going to come, right? So that is let's go to the next phase. So it is already here. So now if I do this one, so that is going to be 0, right? Because if we are going to be orthonormal function, so that means if you do normalization, each individual function that is going to be 1, but there are two different functions, so this is going to be 0, right? So if I do this, what you will realize is that, so that means let me write here. So I'm going to get back here, then after that I will remove this part, right? Okay, so that means this is going to be, as psi1 and psi2 both are real, I'm not going to worry about really that. So this is psi1, this one, right? And then I'm going to get this, so that is going to be C psi1 plus psi2. Of course, there is a multiplication, right? So that is what should be this value. Now this value, if I am going to go for the orthogonality, then this value should be 0, right? Okay, so if I do this, so that means what I get, of course I am having integral and d tau here, right? So that is basically going to be 0, right? Now if I do this, what I am going to get is that C is being constant and I'm taking as a real, so I'm star, I'm removed it, so it's that is C here outside the integral. Then you have psi1 mod square d tau. I'm writing 1 because this is involved with the psi1, so that doesn't make any difference, but that is basically this. Then I'm going to get integral psi1. If you want, you can keep the star because as it is real function, so I'm removing this. Okay, so don't get confused with that. This is psi2 and d tau. So that is going to be 0. Okay. Now, what is the value of this? Look at here, psi1. Psi1 is normalized, right? 1 by square root of 6. 2 into 1 is a minus 1 is b minus 1 is c. So that is a normalized function. So that means this value is, this integral value is going to be 1. Right? Okay, let me remove this, otherwise I'm going to get clumsy. By this time you can think and do it yourself. Okay, it's taking time because I don't want to remove all the annotations, so that I have to erase. Okay, so now yeah, come back to this. So this value, if you are looking at this one, so that is nothing but your 1, right? Because that is normalized function, so that is going to be 1. So that means I'm going to get C equal to minus this part, right? So that is minus integral psi 1 psi 2 theta, right? So that's what you get it. Now what we have to do, we have to work out what should be the value of this, right? So if you look at this, can you figure it out what should be the value? Let me go back and see the function. Then oh yeah, this is I'm overwriting on this, but just look at these two functions. If you multiply that, what is the value you are going to get? So this is 1 by square root of 6. This is 1 by square root of 6. So if you multiply 1 by 6, okay. Now when you multiply these two, what do you get? You get this 2 into 1SA, and then this is minus 1SA. So that is this 1SA, that is again normalized. So you get minus 2 here. Again, this minus 1SB, this is 2 into 1SB. Again, you get minus 2 here, right? So that is minus 2 minus 2. And then if you multiply 1SC and 1SC, you get plus 1, right? So this is minus 4 plus 1, you get the minus 3. So that's what you get it, right? So I'm not going to really do it. You can work it out. I hope you will be able to do it, right? So that is by do this. So this minus and the minus what we get, so that will become plus. So I'm going to get 1 by 6, that is square root of 6 into square root of 6, that is going to be square root of 6, and then I'm going to get into 3. So this was actually minus 3 and this minus, so that makes plus 3. So I'm going to get half, right? So this value is going to be half of this, right? So if you get this coefficient now, then half. So I'm having my new psi 2 prime. Of course, representation is E, is going to be my psi 1, right, into half, right? So that was my function, this one. So half into psi 1, half into psi 1 was again something like 1 by square root of 6, and whatever the value you are going to get. So that is 2 into 1s A minus 1s B minus 1s C, right? So that is psi 1. Then you are going to add up with the psi 2, right? Psi 2 again is going to be 2 into 1s B minus 1s C minus 1s A. Okay, of course you are having square root of 6, the coefficient. Right. If you do simplification, right, I think what you are going to get here is like with the coefficient. I'm not writing the coefficient, so whatever the coefficient, because I have to normalize this, what you get, whatever the coefficient you are going to get, so that coefficient is going to be there. Let's say that is, let's say, n, right? and then what you are going to get is that. So this is going to be, one of them is, let's say one of them is going to get cancelled out, right? Like this half in 2 into 1 SA, so that become 1, and then you are going to have minus 1 SA, right? So this, let me take the other color. So this and this part is going to get cancelled out, right? Then what happened, you have 2 into 1 SB, and then here half, right? Half 1 SB. So it's basically coefficient come 3 by 2 by 1 by square root of 6, right? 6. So I'm going to not going to go for the coefficient because I have to normalize. So this is going to be 1SB and then minus, I'm going to get 1SC, because this is 1SC, and then here it is minus 1SC. So that is also going to be 3 by 2, minus 3 by 2 1SC. So I'm going to get 1SC. Right. So that is the function I'm going to get it, right? Now, of course, this is not again not normalized. So if you normalize this, you can understand that you are having only two functions. So therefore, you are going to get 1 by square root of 2. Right. So that is basically, if you after normalization, if I do this, so the value of this function is going to be, so I'm just removing this. I'm not going to waste time. Yes, Sushrut raised his hand. Let me address his question.
So it should be 3 SB, no?
3 by 2.
When we 3 by 2 and
yeah.
1 by 2 will be taken in common, 3 SB. 3 SB minus 1 SB, 1 SC.
3 SB, no 3 SB. This is, look at here. Just forget about 1 by 6, square root of 6. That is common. Okay. So this is you are going to get 2 into 1 SB, right? And then minus half.
Half into.
So that is 3 by 2.
3 by 2. And half will be taken common as the 1 SC is also half.
No. Again, 1 SC. Forget about that. Look at this. You have this, right? This 1 by square root of 6. That will be as it is. Forget about that right now. Right. So this is 1 SC minus 1 SC, right? And this is minus half 1 SC. So that is minus 3 by 2 1 SC. Okay. Now whatever the coefficient it comes, it doesn't matter. When we normalize it, ultimately you are going to get this. Okay, you work it out. If you don't get it, then we'll discuss it again in the extra time.
Okay, sir.
Okay. So that's what we get it. So finally, what we get is these three functions, right? These are the three SALCs we are going to get it, right? I hope you'll agree with that. So this is A1 type, all positive combination. This psi 1e I have taken as it is. So that is 2 into 1 SA minus 1 SB minus 1 SC. And psi 2 prime, the after doing Smith orthogonalization, what we get, so that is 1 by square root of 2, 1 is B minus 1 is C, right? So these are SLC of different types. Now we have to combine these with the atomic orbitals of nitrogen with this proper symmetry, right? Now, before getting into that, what I would like to draw your attention here, how they are going to look like. Right? That is important, because based on that we can easily figure it out. Right? So let me just draw your attention here. Looking at the function itself, we can see what is going to be the shape of this SALCs. Okay. Okay. Let's go for the first one. Now look at this function. This is whatever this. Now when we are going to go for the probability density, so that is basically square of this, then multiply the volume element, we get the probability, right? So then if we are going to go for the orbital, then we are going to get sum of the square of this, square of this, of this. So therefore, if we draw it, the orbital, so what I'm going to get, I'm going to have this density, and this density. So the resultant is going to be something like this, right? So I'm drawing with the contour like this. Okay, so this is going to be the SALC of A1 type. Okay, I hope you will agree with that. Now, next one, we go for this. Now look at here. This is the coefficient, whatever it is. Now when we do this, now we have contribution double of this for 1SA, right? So that means we will have more contribution when make it square. So 4 times of this, and then I'm having minus of this, minus of this. Now these two are in the same phase, right? So if I go for first one, this one, so I'm having kind of 4 times of density. So I'm making it bigger one, right? And now this is plus combination, plus positive, right? Now these are going to be negative. So I'm having this and this, but they are negative combination. So and the negative combination, but both in the same phase. So what I am going to is like a kind of a dumbbell shape. We are going to get it for this one, but sign is going to be negative, right? Now if you look at here, there is a node along this, so therefore this is going to be kind of px, because my x is like that, going in this direction. Of course, like default one, right? That is there. So it's kind of px. Now if I go for the other one, last one, I don't have any contribution for this, for A, right? So I don't have any contribution, so 0 contribution. I don't have density here, but I am having B minus C. So that means I'm going to have plus for this, so that is plus, and this is minus. Sorry, I have done wrong. This is going to be minus C. Sorry. So let me erase this plus sign here. So that is minus, actually minus C, and this is going to be plus, right? So resultant, what you are going to get is then this is blue. I'm going to go for the minus, and this is going to be plus. Okay. Now look at here. This is again along y-axis. So therefore, this is going to be py. Right. So this itself tells you that the SALC of A1 type is going to be totally symmetric, and this is going to be kind of S orbital. So this remains invariant under all the operations. This is going to be py. That means the psi 1 is going to sorry, px. Psi 1 is going to be px type, and psi 2 prime is going to be py type. So that means these two are going to be doubly degenerate, as if like px and py. Okay. So I would like to stop here, because we are running out of time. We have less than 1 minute. So let me stop here, and if we have any question, then we are going to discuss.